In this video clip, I'm going to show an example of how to solve a combination capacitor circuit. When we solve a combination capacitor circuit, we're looking to find the potential difference or voltage across each individual capacitor and the charge on each capacitor. The relationship between capacitance, charge, and potential difference is the formula Q equals C times V, or the charge equals capacitance times potential difference. We'll solve the problem in a step-by-step fashion similar to what we did with combination resistor circuits. We'll combine individual capacitors in a step-by-step manner until we end up with one single capacitor. We'll then work backwards in order to find the values on each individual capacitor. So we're going to need to start combining capacitors in this circuit. Now, anytime you have 2 or 3 or more capacitors totally in series, we can combine them by adding reciprocals of their capacitance. When they're in parallel, we add capacitance. That's the major difference between capacitor circuits and resistor circuits. Remember, in a resistor circuit, we added resistance in series and added reciprocals in parallel. For capacitors, we add capacitance in parallel and add reciprocals when they're in series. So if we want to rewrite this circuit, I can keep C1 the way it is, and I can combine capacitors 2 and 4 in one step. Now for these, because they're in series, I add reciprocals. So I have a 12 microfarad capacitance and a 15 microfarad capacitance. So 12 reciprocal plus 15 reciprocal gives me 0.15. Hit reciprocal, that's 6.67. And that's in microfarads because that's the unit that we're using. I'll leave capacitor 3 the way it is, and then capacitors 5 and 6 can be added together. And since they are in parallel, I just add capacitances. So C5 is 8 microfarads, capacitor 6 is 10, so 8 plus 10 will be 18 microfarads. Now capacitor 3 is 12 microfarads, 7 is 16 microfarads, and capacitor 1 is 14 microfarads. In my next step, I can combine capacitor 3 with capacitor 5, 6. So I still have capacitor 1. I'm going to leave capacitor 2, 4. And I'm going to combine and get capacitor 3, 5, 6. Now, for this capacitor, because they are in series, I have to add reciprocals. So 12 and 18, clear that, 12 reciprocal plus 18 reciprocal equals reciprocal. Did something wrong. Let me punch that in again. I think I hit the wrong button on the calculator. 12 reciprocal plus 18 reciprocal equals, and then take the reciprocal, I get 7.2 microfarads. That looks better. Now in the next step, I have the two that are in parallel that I'm going to combine simply by adding them together. So I'll have C1, I'll have C2, 4, 3, 5, and 6, and we'll have C7. So when I add 6.67 and 7.2, that's 13.87 microfarads. Capacitor 7 is 16 microfarads, and capacitor 1 is 14 microfarads. Those three are all in series, so to get my total capacitance, I'll add reciprocals. 14 reciprocal plus 13.87 reciprocal plus 16 reciprocal equals, get the reciprocal, 4.85. And that is my total capacitance, 4.85 microfarads. Now the formula that we use, or the relationship, will be Q is C times V. So V is Q over C. So when I find the charge, I multiply capacitance times voltage. So when I take 4.85 microfarads times 48 volts, I get 232.8, and that's microcoulombs. So now I have my total capacitance, that's 232.8, or total charge, microcoulombs, and I have 48 volts on that last capacitor. So then I work backwards. Where did this capacitor come from? It came from these three. How are they arranged? They're arranged in series. What stays the same in series? Capacitance, or charge. Excuse me. Charge stays the same in series. So each of these three are 232.8 microcoulombs. Well, I can put those two values for C1 and C7. 232.8 for C1 and 232.8 for C7. To get the voltage, I'll take charge over capacitance. So 232.8 divided by 14 is 16.63 volts, and 232.8 divided by 16 is 14.55 volts. So I've totally solved capacitor 1 and capacitor 7. To get the others, I need to find the voltage of the capacitor 24356. So I'm going to take the 232.8 volts, or microcoulombs, and divide by 13.87 microfarads, and that gives me 16.78 volts. Now, Kirchhoff's laws are true for these circuits, so if we do a voltage, these 3 volts should add up to equal our 48 volt battery. So if I took 16.63 plus my 16.78 plus my 14.55, it equals 47.96, which is very close to our 48. So then I go from this capacitor and say, well, where did it come from? Well, it came from these two. How are they arranged? Parallel. What stays the same in parallel? Volts. So if this is 16.78 volts, each of these are 16.78 volts. And if I know the voltage and the capacitance, I can find the charge on each. So if I take my 16.78 volts times 6.67 microfarads, I made another calculator error. Q is C times V, so 6.67 times 16.78 is 111.92, and that's microcoulombs for charge. And then I take 16.78 volts times 7.2, and I get 120.82 microcoulombs for the C356 combo. So then you say, well, where did C24 come from? It came from these two. How are they arranged? They're in series. What stays the same in series? Charge. Charge stays the same. So C2 and C4 are both 111.92. 111.92. I That's C2, C4, 111.92 microcoulombs. So to get the volts, I take Q over C, so 111.92 divided by 12 is 9.33 volts, and 111.92 divided by 15 is another calculator error. I need to get a new calculator. This one keeps messing up. 111.92 divided by 15 is 7.46 volts. Notice that if we added those two together, we would get 16.79, and here they are, 16.78. So we finished capacitors 2 and 4. So now we need 3, 5, and 6. So where did capacitor 3, 5, 6 come from? It came from these two. How are they arranged? They're in series. What stays the same in series? Charge. So if this is 120.82 microcoulombs, each of these is 120.82 microcoulombs. Well, that is the charge on C3, so we can put that in our chart, 120.82, and we can get the voltage, 120.82 divided by 12 is 10.07 volts. Then we'll need to find the voltage of capacitor 5, 6, so 120.82 divided by 18 is 6.71 volts. So we've solved capacitor 5, 6. Where did it come from? It came from 5 and 6. How are they arranged? They're in parallel. What stays the same in parallel? Voltage. So they'll each be 6.71 volts. And so to get their charges, we multiply 6.71 times 8, 53.68, and we multiply 10 times 6.71, which I shouldn't need a calculator, 67.1. Now, in our resistor circuits, we could add up all of the powers and they would equal total. We don't have that same kind of check for a capacitor circuit. But Kirchhoff's loop law still holds true. So if our battery was 48 volts, if we add V1 plus 2 plus 4 plus 7, we should get 48 volts. So 16.63 plus 9.33 plus 7.46 plus 14.55 hopefully equals 48. And I get 47.97. So I'm fairly confident we've solved that correctly. I can check one more loop. I can go C1, 3, 6, 7. So voltage 1 plus voltage 3 plus 6 plus 7 should also equal 48. So I'll take 16.63 for V1 plus 10.07 for V3 plus 6.71 for V6 plus 14.55, and that's 47.96. So it again checks out. So I can be reasonably confident that my values in the table are correct and I have correctly solved this combination capacitor circuit.